this video, we're going to walk through the computations for a one sample t-test. Okay, so up to this point, the only test that we've run has been a z-test for a sample mean, and there were certain conditions that needed to be true in order to run the z-test for the sample mean. One of those is that you had only one sample, right? So there was only one sample mean, and the other was that the population variance was known, and by extension, the population standard deviation. Now that's really unusual. Usually we don't know what the population variance is or the population standard deviation. So when there is one sample mean and we do not know the population variance, we run a one sample t-test. Now it's time to introduce the most fun part of this entire video series, and that is the amazing statistics selector. We're going to need a decision tree to help us pick which statistics we should run given our research questions and our research design. So we're going to start off the amazing statistics selector by simply asking how many samples do we have? Well, at this point, we're just dealing with single samples. So our choice is really, do we have one sample or do we have more than one sample? Now let's make a short shrift of having more than one sample. We'll just leave it at this. You're going to do something else other than a t-test or a z-test for a single sample mean. Okay, so we have other statistics for that, and those are coming. But if we have more than one sample, we'll need to use those statistics. Now, let's concern ourselves with just having one sample. Then the question becomes, is the population variance known? If the answer is yes, we do a z-test for a sample mean. If the answer is no, we do a one sample t-test. Okay, now I'm going to go through 10 steps. That sounds horrendous. It's really not that bad. They go pretty quickly. But there are 10 steps really for you to consider when doing hypothesis testing and subsequent theory revision. Okay, first of all, you're going to ask a testable research question. Okay, we have to ask questions that we can actually test using our methods. The second is we're going to define the population, and we get to choose how to do that. We're then going to choose the correct statistical test to run. And we're going to then decide if we're going to run what's called a one-tailed directional test or a two-tailed non-directional test of significance. Those were covered in other videos. And if we choose a one-tailed test, we're going to need to provide some justification for running the one-tailed test. And I'll come back to that in just a moment. We're then going to specify the null and alternative hypotheses, select the size of the region of rejection, or it's also called the critical region, and that's called alpha, so we need to select the alpha level. And then once we've done that, we need to identify the critical values for rejecting the null hypothesis. And by this we mean the cut point at which we say, hey, that sample mean has fallen so far from the mean of the sampling distribution that we reject the null hypothesis. Then we're going to collect data, run the statistical test, and we're going to make a decision regarding the null hypothesis. And if the null hypothesis is rejected, generally we'll calculate an effect size and conduct any additional post hoc tests. Post hoc tests are things that we'll learn in later videos. It's not really relevant for a one sample t-test. Also in this video, I'm actually not going to calculate the effect size simply because that's going to take some additional explanation, and I'll put that in a later video. And then finally, we're going to generalize back to the population and revise subsequent hypotheses for subsequent research studies. Okay, so let's start with step one. Let's ask a testable research question. Now we need to ask a question that can be answered either true or false. In other words, there has to be mutually exclusive outcomes. So the example we're going to work with in this video is, was last September's daily high temperature in Orlando, Florida greater than the historical average? Now that's pretty clearly written, and there are really two possible answers, yes and no. Next thing we need to do is define the population. Now typically when we talk about population, a lot of times we think in terms of humans or animals or things like that. But it doesn't necessarily have to be the case. We could define our population, for example, in terms of daily temperatures, historical daily temperatures. But the main thing is we need to be really clear about the population from which the sample is drawn and to which results are meant to generalize. So in this example, our definition of the population is the daily high temperatures in Florida during September. Okay? So we're going to be taking historical data and using that as the population. So the average historical temperature in Orlando for September is 90 degrees Fahrenheit. That's 32 degrees Celsius. So we would express that simply as mu equals 90. So mu equals 90 is the average historical temperature in September in Orlando. Now we need to choose the correct statistical test, and we have a hint already. Obviously, we're going to be doing one sample t-test, but the step here is to choose the correct one. Sometimes it's not simply given to you what test to run, right? So how many samples do we have? Well, in this example, we have just one sample. Okay, it's going to be a sample of temperatures from the most recent month in September. Is the population variance known? Well, because we want to do an example of a one sample t-test, we're going to say no, we don't know the population variance in this case, okay? But we do know the population mean, so that's given to us. So our selection then becomes a one sample t-test. Okay, now we need to select whether we're going to do a one-tailed or two-tailed test of significance. Usually, we're going to assume that we should do a two-tailed test of significance unless there's a really good reason to run a one-tailed test. For example, if it's just inconceivable that the results could err on one side of the sampling distribution, we would choose a one-tailed test. If there's just research that tells us that historically it just never occurs that we'll find a sample mean on one particular side of the sampling distribution, those would be good reasons to run a one-tailed test. So a question we should just ask is it feasible that the sample mean could be above or below the population mean? And yeah, it could be either way. In this case, we don't know for sure that the sample mean will be higher than the population mean, in other words, higher than 90 degrees. It could be lower than 90 degrees. So, so the answer to the question, could temps in Orlando this year have been hotter or cooler than the average temps? Yeah, it could have gone either way, right? So it's not obvious to us that it'll be on just one side, either above the mean, hotter, or only cooler. So we're going to go ahead and choose a two-tailed test of significance. That's a non-directional test. Then we're going to specify the null and the alternative hypotheses. Okay, so the null hypothesis is going to be that the mean for our sample simply equals the mean of the population, or 90 degrees. So the notation here, when it says mu equal 90, what that means is that we're using a sample of temperatures from this past September to represent the larger population of temperatures from last September, and that's what we're really interested in, right? And what we're saying is that September temperatures, all of them, were equal to the historical average. So the mu of those September temperatures equaled 90, which was the mu of the historical average. Now the alternative hypothesis is that the mu does not equal 90. Okay, so the sample is representing a population that looks different than the historical average. Okay, look at this. We're already up to step 6. We're making good time. So now we have to select alpha, and we're going to generally assume that alpha should be 0.05. That's the custom, unless there's a really good reason to modify that. And sometimes there are good reasons. Sometimes you really don't want to have a false alarm, or sometimes you really don't want to have a miss. It all comes down to type 1, type 2 errors. But in this case, there's no compelling reason to change alpha, so we're just going to select 0.05. So that's the size of the region of rejection, the critical region. Okay, now step 7, we have to identify the critical values for rejecting the null hypothesis. As you know, with a z-test, it was pretty easy to do that because all we needed to do was identify the cut points or the critical values on either side of the sampling distribution. That turned out to be plus or minus 1.96. So we would say that z-crit, or the critical value for z, was plus or minus 1.96. The problem is with a t-test, we actually need to look up the critical values. And you might ask, why? Why do we need to look up the critical values? Why can't we just go ahead and do what we did with a z-test for a single sample mean? Well, it takes a little bit of explaining, but it involves the tails of the sampling distribution and something called degrees of freedom. Now, in a previous video, I talked a little bit about degrees of freedom. Imagine that we were sort of randomly sampling temperature values from September. And we decided we're going to take 5 temperature values out of the month of September. Well, when I collect that data, I have the actual observations, right? So this would be 95 degrees, 98 degrees, and so forth. And then I would also be able to sum up all of those temperatures to get a total score, which would be 474. Now, here's the thing. Once I know the total score and I have all but one of the observations, that last observation, the value of it, where the question mark is actually completely dependent on what came before, right? So if I know the sum is 474, if I just added all those temperatures together, then this has to become 93, right? Because now if we add 93, we get 474. Okay, so what that means is that only some of the observations, all but one of the observations, are free to vary. And that's one of the assumptions of our analyses, is that each observation is a sort of randomly drawn from the population. So the values should not be dependent on any other values in our data set. Okay, so in a single sample t-test or one sample t-test, the degrees of freedom, which we call DF, is equal to n minus 1. Okay, now this is going to come into play as we start finding the critical value for t. With smaller degrees of freedom, the shape of the sampling distribution is flatter than a normal distribution, and it has thicker tails. And the central limit theorem told us this would be the case. So if you recall the central limit theorem, it pretty much said as n approaches infinity, the shape of the sampling distribution becomes increasingly normal, right? So that implies that with small n's and correspondingly small degrees of freedom, the shape of the sampling distribution is less normal. So degrees of freedom matter when we're determining the critical value for t. And then the question is, okay, so what effect does that have? I mean, why is this important? So let me show you some graphs here. Okay, here's a graph of a sampling distribution where we have a very large n and correspondingly a large number of degrees of freedom. Okay, it takes on a normal shape, and this is actually the case when we're dealing with when we do know that population variance and standard deviation, that the cut points for z will be plus or minus 1.96. Okay, so the region of rejection then is this red area on either side of the sampling distribution in the tail. Okay, but now in the case where we don't know the population variance, and let's say we shrink the sample size, okay, let's say now we only have 20 degrees of freedom, so our n equals 21. Look what happens to the tail. There's more area in the tail. This brown area gets added in the tail, right? And then if we go down to really small degrees of freedom, even more area goes into the tail, right? So if we just kept our cut point, the critical value at plus or minus 1.96, look what happens when all of this area is now added to the tail. We actually have more area in the region of rejection than we really expected to have. And so the question is that amount of area, does that really amount to 0.05 of the area under the curve, or is it more than that? So because sample means are more variable when degrees of freedom is small, okay, what happens is the distribution gets flattened out, more platykurtic, okay? So because sample means are more variable when degrees of freedom is small, that means there will be more area in the tails of the sampling distribution than the alpha level would indicate. And so the problem we run into is that the area in the region of rejection actually is greater than the set alpha level. And this has the effect of inflating the true type 1 error rate. So even though we might think the type 1 error rate is equal to alpha, 0.05, actually it's not, because with small n's and small degrees of freedom, we're increasing the size of the tails, right, the amount of area under the tails, which in turn makes it more likely that we would reject the null hypothesis incorrectly and make a type 1 error. Okay, so the total amount of areas in the tails is increasing as we get smaller degrees of freedom. So we need to make a correction. And the correction is to push the critical value for t farther into the tails of the sampling distribution. Okay. And the effect then is to reduce the amount of area in the region of rejection and to return the true alpha level to 0.05. And you're probably sitting there thinking, oh, the math for this must be ridiculously hard. So how do we do this? Here's the really good news. As you're learning how to do this, it's simply a table lookup. So I just need to teach you how to look it up in a table. You don't have to do any math at all, which is very good news. Right? Now, in every textbook, you're going to find a table that looks like this. I got this one off of researchgate.net, and the source is below if you want to use that, below the table. But every stats book is going to have this kind of table. And basically what you do is you just index the degrees of freedom in your analysis against the amount of area or the alpha level that would be in one tail of the distribution. Okay, so we know from our example, we had 5 observations, right? So we have 4 degrees of freedom. Okay, so we look across this row. Now we had set alpha at 0.05. And when you're doing a two-tailed test, if alpha is 0.05, then that means that in each tail, there is 0.025 of area under the curve, which would put it right here. Okay, now we just look for the intersection of the row and the column, and that becomes 2.776445. That's a lot of digits to carry out. And then the critical value for t, we'll just round up, is going to be plus or minus 2.78. So by adopting that critical value for t, we return the true size of the region of rejection back to alpha equaling 0.05. Now, one thing I just want to make a note of real quickly here. You'll notice that when we talk about a t distribution table, which is what this is, we need to think of the t distribution as a family of distributions, right? That really depend on degrees of freedom, right? Because each of these rows represent different sample sizes, right? Because degrees of freedom is just n minus 1. So the values for the critical, the value that'll show up for the critical value is completely a function of how big our sample size is and the corresponding degrees of freedom, right? So if we change that, then we're going to have to do a new lookup. So what that means is that there's a family here of t distributions that we're concerned with, not just one t distribution for the for sampling error. Okay, so here we go. We're going to now collect the data and run the statistical test. We're ready to go. We're going to collect our data, and then we're going to do a whole bunch of computations that I will walk you through. We're going to need to calculate the sample mean. We've got to do sum of squares. And because we don't have the population variance, we've got to estimate that. And then from that, we'll calculate the estimated population standard deviation. And then we're going to go calculate the estimated standard error of the mean. And then finally, the t statistic, which is what we're really interested in. Okay, now as we're going through this, I'm going to show you 2 ways of calculating sum of squares. One is a tabular format, and then the other is using a sum of squares computational formula. So I'll show you both ways to do that. Okay, once we do all the computations, then we have to compare the obtained t-score, the t-statistic we've calculated, to the critical value for t, and we're going to then make a decision regarding the null hypothesis and then write it up in APA format. So here's our data. We have 5 days of observations that were randomly drawn from September. And here's the temperature that came out, 95, 98, 96, 92, and 93. Okay, so let's do the tabular approach first. So in that first column, we have the sample of temperatures that we have collected, which I just showed you. And then the next thing we're going to do is calculate the mean of that sample. So that's the sample mean. And then once we do that, we're going to calculate the deviation score. Okay, and the deviation score is simply the difference between any one observation and the mean of all the observations. Now, if we summed up all of those deviation scores, we would always end up with 0. Okay, so to get around that problem, we're going to square each deviation score. So 0.2 times 0.2 is 0.04, 3.2 times 3.2 is 10.24, and those become the squared deviation scores. Okay? Okay, and here's our next step. Here's everything we've already done up here in the white section of the table. And now what we're going to do is we are going to calculate or compute the sum of squared deviations, or it's simply called the sum of squares. And most of the time you'll see that just notated as SS. I actually put the formula there for you, but a lot of times you'll just see it as SS. Okay, and that's just, we're just going to add together everything in the column above it, right? And that comes out to 22.80. The next thing we have to calculate is the estimated population variance. Okay, now the estimated population variance is simply our sums of squares divided not by n, which is 5, but by degrees of freedom, which is 4. Okay, and when we do that, we get 5.70. Now the last thing we have to do is get the estimated population standard deviation, and that's simply the square root of 5.70, and that value comes out to 2.39. So that's really sort of the first step in terms of what we want to do. Now what I'm going to do is I'm going to show you how to use the computational formula to calculate the sum of squared deviations. This is going to give us the same result, it's just a little different way to do that. And what we do is we take our x values, those daily temps, right? And the first thing we do is we just sum them. So we get 474. Now what we're going to do is we're going to square each of those daily temps. So 95 times 95 is 9,025. We do that for every single x. And the sum of those squared x's is 44,958. Okay, so we need that to start. And next we're going to actually compute the sum of squares using the computational formula. So there's the computational formula, and all we're going to do now is we're going to plug in numbers. Okay. So 44,958 is the sum of x squared. Okay, then we're going to put the sum of x's, the 474, and square that in the numerator. We're going to subtract that out after we divide by n, 5. And so then the question is, well, what do we get? And the answer is 22.80, which is exactly what we got in the tabular format as well. So those are just two different ways of computing sum of squares. It gives us the same answer. Okay, now we're getting to the really fun part. Again, what was the historical average of temperatures in September in Orlando? It was 90 degrees. And now we've just got to do two things. The first is we've got to calculate the estimated standard error of the mean, and then we're going to calculate the t-statistic, what we'll call it t-obtained, the t-statistic, and that'll tell us how far from the population mean of historical averages, 90 degrees, our sample mean fell. Okay? So we need to start by plugging in numbers. So the estimated standard deviation was 2.39. Our n was 5, and that works out to be 1.07. Now, what are we going to do with that 1.07? That's the estimated standard error of the mean. Well, you can see it, right? It's right here. It's in the denominator of the calculation for our t ratio, okay, the t statistic. So we're going to plug it in right down there. And then all we've got to do is take our sample mean, which we had computed earlier, and subtract out the 90, which is the mean for temperatures historically in Orlando. So 94.80 minus 90. Well, that's going to reduce down to 4.8 over 1.07, which becomes 4.50. So what is this? And again, these are in standard error units, right? So what this means is that the sample mean that we've observed is positive 4.50 standard errors from the mean of the historical averages in Orlando for high daily temperatures in September. Okay, so that's a lot. We know that that's a lot, but we just don't know quite yet whether we should reject the null hypothesis. So what we have to do is we have to compare our obtained t value. Okay, that's the t statistic we call the t ratio. But as we're running the problem itself, we'll call it t obtained. And we're going to compare that to the critical value for t. So as a refresher, our critical value for t was plus or minus 2.78. Remember, that was the value we looked up in the table. Okay, so 2.78. And what was our t obtained? Well, this is what we actually calculated, what we just finished doing, and that was positive 4.50. So the question is, do we reject the null hypothesis? Well, it'll be clear if I just go ahead and show you the sampling distribution if we assume that the null hypothesis is true. Well, here's our sampling distribution, and the mean of this sampling distribution is going to equal the mean of the historical daily temperatures, right? So 90. Now, we also calculated the estimated standard error, right? So if we added one estimated standard error, that becomes 91.07. We do it again, it becomes 92.14. We do it again, 93.21. So a value of 93.21 is 3 standard errors from the mean of the population when we're assuming the null hypothesis to be true, okay, that the population mean should be 90. Okay, now let's locate one of our critical values. We know that that was negative 2.78. We'll do it on the other side because we're doing a two-tailed test, so that's positive 2.78. And now the only thing left to do is to locate where our obtained t-value, the t-statistic we actually calculated, where does that show up in this distribution? Well, if I were to drop it in the distribution, it almost goes right off the graph, right? I'd put it way over here, a positive 4.50. And that corresponds to our sample mean of 94.80. Now, what's really clear is that the region of rejection is the non-shaded area. So everything not in red, right? So it's here and it's here in the tails. So clearly, t obtained falls in the region of rejection. Now let's go back to the notation for our null hypothesis and alternative hypothesis. If you recall, the null hypothesis was that the sample mean that we would observe, which represents a larger population mean, should equal 90. And the alternative hypothesis is that it would not equal 90. Well, this sample mean, we can tell for sure, is so far from the population mean of historical averages that it's unlikely to have been drawn by chance, okay, or it's unlikely to fall that far away from the population mean due to sampling error. So the alternative hypothesis seems to be supported, and we are justified in rejecting the null hypothesis. We do not think that it's all that likely that just based on chance or sampling error, we would observe a sample mean this far from the historical average of the population of daily temperatures. That's unlikely that we would just randomly draw that sample mean from the sampling distribution when we assume the null hypothesis is true. We just don't think that that's going to happen probabilistically, so we are going to reject the null hypothesis. Now, if our sample mean had fallen, say, somewhere in here, in the red shaded area, then we would fail to reject the null hypothesis. Okay, and then really the last thing that we need to do is to write up the result in APA format. Okay, and APA does have a format for every statistical test that's out there, and so I'll just go through and show you the general form and then show you what it would look like. Typically, for these kinds of tests, we note the type of test, and then we put degrees of freedom in parentheses. We report the test statistic. In this case, it's the t ratio, the p-value, the probability that the observation was due to sampling error, and then finally effect size, but I'm going to skip the effect size part for now. So when we'd write this up, it would be t, and notice that the t is italicized, and then 4, so 4 degrees of freedom. So that tells us we ran a t-test with 4 degrees of freedom, and that the obtained t, or the t ratio, was 4.50. And then the probability of this result occurring by chance or sampling error was less than 5 in 100 because the sample mean was located in the region of rejection. So you have to just make sure that you have the less than sign included in your notation very clearly, and it's pointing the right direction, because anytime it's pointing toward P, it's the less than sign, you're implying that you rejected the null hypothesis. Okay, couple of quick notes before we finish. First of all, statistical programs will provide you the exact p-value, and many textbooks will show you how to look up the exact p-value. It's not hard to do. You know, basically what you do is you look up the obtained t, and you can find that within a t-distribution table, and it'll help give you the probabilities and a sign. I just didn't do that for you here, but textbooks will generally show you how to do that. It's fine to report the exact p-value as a statistical program. Will give it to you, but even if you just said p is less than 0.05, that would be correct as well. And the effect size calculation, which isn't included here, that's going to be the subject of another video using the same example, and we're going to be looking at Cohen's d. There are a variety of different types of effect sizes that we'll be discussing in statistics. Cohen's d is often used with t-tests, so but we'll deal with that later. It would have added just too much time to this video to do it here, but I'll make a separate video for that. So big picture, the one sample t-test is used when we have a single sample and we know the population mean, but not the population variance. There's a whole series of steps, remember there were 10 of them, that we must go through whenever we're conducting a hypothesis test. And so, and then the last one, this 10th step, which I didn't really talk too much about here, is to then take a look at the results, go back and reevaluate any theory that might be affected by those results, and then design new hypotheses. And that's sort of the feedback loop of the whole scientific process. But there's really 10 steps that we go through whenever we're conducting a hypothesis test. Now, the critical value that defines the region of rejection for a t-test is a function of the degrees of freedom, the selected alpha level, and really the type of test that we're running, whether it's directional or non-directional. And if the obtained t statistic is farther from the population mean of the sampling distribution than the critical value is, then we're going to go ahead and reject the null hypothesis. So that's pretty much it for showing a one sample t-test. And I have another video in the series that shows you how to do it with Excel and then also with JASP, and you might want to check that out as well.